We are told the Earth is 4.54 billion years old. That number appears in textbooks, documentaries, and museum exhibits. But here is an honest question. How does anyone actually know that? No one was there with a stopwatch. No written records exist from the Hadean Eon. So how did science pin down the birthday of our planet? The answer is one of the greatest detective stories in the history of science. It involves a doomed physicist, a forgotten genius, a heroic geochemist who built the world's first clean room, and a handful of space rocks. Welcome to Grossdenken, my friends. In today's video, we are going to walk through the 3 major steps that cracked the case. The failed attempts, the discovery of radioactivity, and the final brilliant solution using meteorites. Please support this channel by just subscribing. That would mean a great help. Our story begins in the 19th century with the famous physicist William Thomson, better known as Lord Kelvin. He was one of the smartest people alive. He helped formulate the second law of thermodynamics. He worked on the transatlantic telegraph cable. His word carried enormous weight. In 1862, Kelvin turned his attention to the age of the Earth. He assumed the planet began as a completely molten ball of rock. He calculated how long it would take for that ball to cool to its present temperature using known physics of heat conduction. His answer? Between 20 million and 400 million years. Later, he narrowed it down to under 100 million years. This caused a major problem. Charles Darwin's theory of evolution by natural selection required vast stretches of time, far more than 100 million years. Geologists studying layers of rock also felt the Earth was much older. But Kelvin was a titan of physics. Who were they to argue? Then, in 1896, everything changed. Henri Becquerel discovered radioactivity. Soon after, Marie and Pierre Curie isolated radium and polonium. In 1903, Pierre Curie and Albert Laborde made a shocking announcement. Radium produces enough heat to melt its own weight in ice in less than an hour. This was devastating to Kelvin's cooling calculation. The Earth was not just a cold corpse slowly losing heat. It had an internal heat source, radioactive decay. Kelvin's cooling model had been built on a false assumption. The story goes that in 1904, the physicist Ernest Rutherford gave a lecture with Lord Kelvin in the audience. Rutherford knew his findings contradicted Kelvin's. As he later recalled, he saw the old bird sit up and glare at him. Then Rutherford had an inspiration. He said, "Lord Kelvin limited the age of the Earth, provided no new source was discovered." That prophetic utterance refers to what we are now considering tonight, radium. Kelvin beamed at him. The old age was dead. The hunt for a new number began. But how do you actually measure billions of years? You need a clock. And nature provided one inside certain minerals. Take the mineral zircon. When zircon crystals form, they love to incorporate uranium atoms into their structure. But they strongly reject lead, so a newly formed zircon contains uranium, but almost no lead. Over time, the uranium inside the zircon decays into lead at a known constant rate. The half-life of uranium-238 is about 4.47 billion years. By measuring the ratio of uranium to lead inside the crystal today, geologists can calculate exactly how long ago the crystal formed. It is like an hourglass where the sand is uranium and the lead is the sand at the bottom. Using this method, scientists have dated zircons from the Jack Hills of Western Australia. The oldest are 4.44 billion years old. That tells us the Earth must be at least that old. But note, that is just the oldest crystal we have found. The planet itself is slightly older. So how do we get from 4.4 billion to 4.54 billion? Enter Clair Patterson, a geochemist at Caltech. In the 1950s, Patterson realized that Earth rocks were unreliable for dating the planet itself because plate tectonics and erosion had recycled the crust. Instead, Patterson looked to the skies. He analyzed meteorites, specifically the Canyon Diablo iron meteorite from Arizona. The logic was elegant. Meteorites are leftover building blocks from the early solar system. They formed at the same time as the Earth, but they have remained chemically undisturbed for billions of years. Patterson used a technique called lead-lead dating. He measured the ratios of different lead isotopes, specifically lead-206 and lead-207 in the meteorite. He then compared them to lead isotopes from deep ocean sediments, representing the Earth's mantle. In 1953, Patterson finished his analysis. The number he got was 4.55 billion years, with a margin of error of about 70 million years. This number has remained remarkably stable ever since. One fascinating detail. Patterson had to build one of the world's first ultra-clean labs to get this right. Lead was everywhere, in the air, in the water, in his equipment. It contaminated his samples. He had to acid wash everything and distill all his chemicals. His quest to date the Earth accidentally made him a pioneer in the fight against lead pollution. So here is the final timeline. The oldest solid material in the solar system, calcium-aluminum inclusions in meteorites, date to 4.567 billion years. Earth formed shortly after that, likely around 4.54 billion years ago during the Hadean Eon. The oldest zircon crystals we have found solidified about 4.4 billion years ago, just a few hundred million years after the planet was born. So how do we know the age of the Earth? We measured the ticking of atomic clocks inside space rocks. We corrected the mistakes of geniuses like Lord Kelvin. And we had a determined scientist named Clair Patterson who fought against contamination, skepticism, and lead dust to give us a number that has stood for over 70 years. The Earth is 4.54 billion years old. Not a guess, not a story, but... Thanks for watching. If you want more deep dives into how science actually figures things out, hit subscribe.